Hello everyone. So today we're going to talk about Lab 6, which is on the Michaelis-Menten enzyme kinetics of lactate dehydrogenase. So by the end of this lab, you should be able to construct a full Michaelis-Menten plot as well as a Lineweaver-Burke plot for LDH. And use a direct hyperbolic Michaelis-Menten fit and also a Lineweaver-Burke. You should be able to extract the Km and the Vmax. You need to be able to compare and contrast both the benefits and the drawbacks of both the direct fit and the Lineweaver-Burke fit. Then you'll need to interpret these kinetic data in the presence of an inhibitor, as well as without an inhibitor, determine what type of inhibition is going on, and then also determine the inhibition constant, or the Ki. And then finally, you should be able to describe the relationship between enzyme concentration and the Michaelis-Menten parameters, so Km and Vmax. Now, hopefully, this will be review or concurrently with most of you who are taking biochem. But if not, you should have a better idea and be better prepared for class after hearing this lecture. All right, so let's start with a schematic of the LDH reaction, which is the basis of our Michaelis-Menten kinetics. All right, so when we start out the reaction, we have LDH, lactate, and NAD+. And up to this point, we've been representing this reaction with an arrow, like so. All right, so this reaction can interconvert between either side depending on the pH, but we've represented this as one concerted step. However, in reality, the enzyme reaction is actually a little bit more complicated than the way I've represented this, because there's the step where LDH actually has to bind the substrate and the cofactor, NAD or NAD plus and lactate. So this would be represented by the K1 value, or the K1 rate constant, or the rate constant of binding. And there's also the fact that although lactate and NAD plus are going to be binding LDH, there's also the likelihood that those substrate and cofactor are going to actually pop back off the enzyme. And so this first step, where LDH goes from being LDH plus its substrate and cofactor to the LDH substrate cofactor complex, this is in an equilibrium, and there's going to be a lot of back and forth between whether this LDH is bound to its substrates or whether or not LDH is surrounded by its substrates. Then, after LDH binds its substrate and cofactor, it's primed to actually perform the chemical step, also known as the committed step, and also known as the hydride transfer, the hydride transfer, depending on which part of the reaction you're looking at. And this is our K2 step here. So when we're measuring the LDH activity or the reaction velocity or the rate, so that micromole per minute, we're actually measuring the whole reaction. However, when we're measuring the reaction kinetics, we want to make the assumption that what we're measuring is the chemical step. So the idea is that the binding of lactate to NAD, the binding of LDH to lactate and NAD plus is relatively fast, whereas the chemical step or the concerted step is relatively slow. And so we can make conditions in our reaction. So we're measuring the chemical step or the committed step or the rate determining step by changing the concentration of the substrate, concentration of the enzyme, and as well as what the identity, as well as the speed of the committed step, because which step of the enzyme reaction is going to be rate determining is going to depend on the reaction. So every enzyme is different, but one thing that we want to try to do when we're measuring enzyme kinetics is we want to minimize this back step here. So we want to minimize the amount at which the substrate and cofactor are popping out of the enzyme pocket to ensure that the reaction that we're monitoring is in fact the forward reaction. And so the way that we can do that is to have a really high substrate concentration relative to enzyme. And in the case of the forward reaction, we can keep the reaction at a high pH to ensure, again, that the forward reaction rather than the reverse reaction is favored. And so by keeping the high concentration of substrate relative to enzyme, so we're talking a several orders of magnitude OOM difference. We ensure that at any time the enzyme is bound, that the enzyme, we can ensure that the substrate and the cofactor aren't popping out of the enzyme pocket. So when we're measuring enzyme kinetics, we're seeing how the rate of enzymatic reactions are changing with the concentration of the substrate. We can see how they change with pH, with salt, and with temperature. Today, or for this week in particular, we're going to be concerned in particular with how reaction kinetics change with the presence of an inhibitor. And one of the reasons why we care so much about kinetics, specifically with an inhibitor, is that many drugs are enzyme inhibitors. And so by studying the Michaelis-Menten kinetics of an enzyme inhibitor, you can learn and get practical experience with some of the vocabulary that you were to see if you were to be reading in the literature about drugs or small molecule drugs that are enzyme inhibitors. So that's why we're focusing on using an inhibitor today. So the rate of a chemical reaction is dependent on many different things. And one of those things is on the concentration of an enzyme. So again, assuming that we are in the linear range when we measure this, if we were to graph the initial velocity, so again, the initial velocity, if we have the change in absorbance per minute, we have our curve there, the initial velocity being that initial linear portion of the enzyme right there. If we were to graph the initial velocity against increasing LDH concentration, what you would see is that relationship would be linear. And so we can manipulate how fast our rate is and where it's in the place where we want to measure it based on the concentration of our enzyme. And so that's what you guys did during lab 2 and 3 and 4 when you had to play around with your enzyme concentration so you could get a line or a reaction velocity where the reaction was steep enough that you could measure the initial concentration and have it accurate measurement so it wasn't hanging out in the noise, but it was also low enough that you could actually catch a linear portion of that curve. So, and the concentration of the enzyme matters. The other thing that matters is the concentration of the substrates and the cofactors. So in our case with NAD+ and lactate. And so again, with Michaelis-Menten kinetics, we're measuring, this is a little bit simplistic, but we're measuring the affinity or the ability of an enzyme to catalyze a reaction using its substrates. And so when we have two substrates this gets a little more complicated. And so what we do when we're measuring with two different substrates is we're going to have to hold, is you hold one constant and you examine the other. And so in this case, our NAD plus concentration is going to be constant throughout the lab. However, what's going to change is our concentration of lactate. So by varying the concentration of lactate, we can determine the affinity of LDH for lactate as well as the maximum velocity of the reaction when we vary lactate. So what happens, so if we're holding NAD plus constant, when we have low concentrations of lactate, the reaction velocity is going to increase with increasing concentrations of lactate. Okay? And so what happens here is that, so if we have a constant, so if this is our velocity at, let's say, 10 millimolar lactate, that's just an arbitrary number, as we go down in concentration, the velocity that you measure is going to decrease. And this is because LDH, think about this conceptually, LDH needs time to hunt for NAD plus and lactate. All right, and so when there's not a lot of LDH, when there's not a lot of lactate and NAD plus around, LDH is going to take more time, and the harder LDH has to search for its substrate and cofactor, the less substrate and cofactor is available, the slower that rate is going to become. And so in this case, when we're at low concentrations of lactate, the velocity is going to depend on the substrate concentration. All right, so that again, yes, the velocity is going to depend, and it's going to increase, or is going to increase with increasing concentration, or decrease with decreasing lactate concentration. However, when we get to really high concentrations of lactate and NAD+, specifically saturating conditions, what's going to happen is you're going to notice is that once you get past a certain lactate concentration, that slope, or that reaction velocity isn't going to change very much. So if we draw a line there representing that cutoff point, and you're going to notice that even though you keep increasing your substrate concentration, the changes you're gonna see in your velocity are going to get gradually smaller and smaller until they level out. And what happened? We at this point we call this saturating conditions, because what happens at this point is you have so much substrate. You have so much substrate that LDH doesn't have to work to find lactate. All right. And so because of this, that means at any given point in time, LDH is always going to be bound to its substrates. So at any given point, as soon as the reaction turns over, boom, there's going to be another lactate and NAD plus in that pocket. And so because there's so much presence, that at any given point in time, that complex is going to be formed, and so it's not possible to fill up the enzyme with any more substrate, so it can't go any faster because it's going to be limited by the turnover of the rate determining step, rather than how long it takes the enzyme to actually find the substrate and the cofactor. And so that's why we call this saturating conditions, because the active site of LDH is saturated. It can't be any more filled with substrate and cofactor. And so, um, and so we can think, of this, and then the speed or the velocity that the velocity that the enzyme approaches when it's 100% saturated with substrate is known as the Vmax, or the maximum velocity. And we never actually achieve Vmax. That's because Vmax can be thought of like a limit, is actually a limit, like a limit that we you learned about in calculus class way back in the day, and that's that the enzyme is theoretically approaching its maximum velocity, but it never quite gets there. All right, and so again, low concentrations, the enzyme has to work to find its substrate and cofactor, so the velocity we see is going to be dependent on how much substrate and cofactor is around. But once we achieve saturating conditions and all of the enzyme is filled with substrates at any given point in time, the enzyme velocity that we measure no longer becomes dependent on how much substrate is around, and instead it's just dependent on the chemistry. And as a result, when you keep throwing in increasing substrate, the velocity isn't going to change. It's just going to keep approaching. It's going to flatten off and start to approach its theoretical maximum limit, or the Vmax. So practically speaking, let's talk a little bit more about Vmax and Km, these terms that I just told you about. So what I have here is what a enzyme kinetic full curve would look like in the laboratory. So we have the rate in micromole per minute. Whew, I'm going to sneeze. On the y-axis, and then we have our concentration of substrate. In this case, NAD plus on the x in millimolar. And so what we can see here is we see manifested that when we're at low concentrations of NAD plus, that curve is really steep, and that's because when we're below, say about 5 millimolar NAD plus, the reaction rate is going to be highly dependent on the substrate concentration. However, once we get past like 5 to 10 millimolar NAD plus, you can see here that we've saturated the enzyme, because the rate at 5 millimolar NAD plus and the rate at 20 millimolar NAD plus is almost the same. And so that means once we've achieved this area of concentration of substrate, we've become saturated. So in terms of definitions, the Km is merely the substrate concentration at which the enzyme achieves one half Vmax. And so we can determine the Km. If we were to look at a Michaelis-Menten plot, we can determine it from the fit, and we'll talk more about how to do that, but you can get a visual estimation by figuring out, say, okay, here's Vmax. Vmax is coming in at around 55 to 60 Vmax. And if we go down So if we're approaching like 60, 60 divided by 2, so 1/2 Vmax divided by 2 is 30, around 30. And so we can go here on the X, we can draw a line over and then extrapolate down, and we can see here that our Km is probably around like 2 millimolar, 1 to 2 millimolar, somewhere in there. And again, Vmax is the maximum enzyme velocity. And again, this is a theoretical number, so it's the velocity that we can think of this as the velocity at an infinite substrate concentration. So again, it's the limit, so it's the velocity was when the substrate concentration equals infinity. And then we can figure out the Vmax from the top of a hyperbolic fit. So you can see here that hyperbola, again, the Vmax comes from the top. So when we pull out the Vmax from a fit, the value that we get, like those initial velocities that you measured in previous labs, you're going to be measuring the micromole of substrate produced per minute. But there's another term that we use very frequently, and this is called the kcat, which is also the turnover number, also known as the turnover number. And so the thing about the Vmax is that one of the disadvantages of using a Vmax is that the Vmax, it depends on the enzyme concentration because it's a velocity. So if you and another lab group have a different dilution for your Michaelis-Menten kinetics, and so your enzyme concentration is going to be, your LDH concentration is going to be different, you're not going to be able to directly compare your Vmaxes because you're going to have different enzyme concentrations, and as a result, you're going to have a different velocity, and you're going to have a different Vmax. You're going to have different maximum velocity that the enzyme can achieve based on the concentration. So Vmax isn't always useful for comparing two different studies. And so for that, we use the kcat, or the turnover number. And so with the turnover, the Vmax is equal to the kcat, or the turnover number, times the total enzyme concentration. And so what happens is, if we know the enzyme concentration, what we then can do is we can take the micromole per minute, or the units were got to be the micromole of, I guess in this case, lactate per minute. And then what we do is we divide that by the micromole. Let's erase that for a sec. So the Vmax is equal to the kcat times the enzyme total concentration, the ET. So if we have the Vmax and if we know the ET, we can then solve for the kcat. So, oops, now I made a highlighter. So in this case, if we have the Vmax and the ET, the kcat is equal to the Vmax in micromole per minute divided by the micromole of enzyme, the total micromole of enzyme. And if we know that we've achieved saturating conditions, and we can make that assumption that at any given point, the total enzyme is all going to be bound to substrate at any given point in time, then we can estimate the kcat. And we can only do this if we have the Vmax, because at the Vmax, all of the enzyme is going to be saturated and taken up with substrate. And so the result of kcat is that the micromoles are going to cancel out, and that gives us a unit in minutes to the -1. As you can see, this is just a minute. This is a turnover, and this gives us the number of reactions per second. And so by taking out that molar component, that dependence on the concentration of enzyme, you can compare your turnover number to somebody else's, because now you don't have to worry about slight differences in concentration that may come from the sample, or maybe the method that you use to measure the concentration of the sample. So I've talked a little bit about the direct fit and about different types of ways of extrapolating Michaelis-Menten data. And so now, when we've gone through and you've measured the enzyme velocity as a function of concentration, you want to determine the maximum velocity and affinity of LDH for its substrate. I'm going to talk about the two different ways that you can use to plot and fit your data to get the Michaelis-Menten components. And so the first way is the direct fit, or the substrate saturation curve. And we call it a substrate saturation curve because, as I've shown you earlier, at low concentrations you have that steepness, but as you approach higher concentrations of substrate, the curve starts to flatten out as you achieve the theoretical maximum velocity, or the Vmax. And one of the the main advantage of the direct fit is that it quite simply is a direct fit of your data. Your data are in its most pure, unadulterated form. So you don't have to do anything to manipulate your data to get the answers that you want. However, one of the disadvantages of Michaelis-Menten is that Michaelis-Menten direct fit is that you need fancy graphing software. So in our case, we need Michaelis-Menten Kinetics. And back in the day, this wasn't easy to do. Like, even now, you can't just do this in Excel. You have to download something to do this for you. And so that's one of the main disadvantages of the graphic software, of the direct fit, is that it takes a little more work to do the fit. And so the hyperbolic fit that we can apply to our kinetic data is y is equal to the Vmax times the substrate concentration. Again, substrate concentration is our x, so that's going to be our variable, our x variable, our constant variable, and the velocity is going to be the y, or the s is the independent variable, and then the velocity will be the dependent variable. And then we divide this by the Km plus the substrate concentration. And so in terms of a hyperbolic fit, y equals ax over b plus x, where a is again the Vmax and b is going to be the Km. The other method we can use to extrapolate our kinetic data is using the Lineweaver-Burk plot, get rid of that E, or the double reciprocal plot. And so the reason why this double reciprocal plot was developed is because back in the old days, there were no computers. And so it was really hard to do a hyperbolic fit by hand. And so back in the day, when you needed to fit a curve, what you did is you linearized your data. And you could do this by taking 1 over the x versus 1 over the y. And when you take 1 over the x and 1 over the y of a curved fit, it gives you a line. And so you can see that here. So our x-axis for a Lineweaver-Burk would be 1 over the substrate concentration, and our y would be 1 over the velocity. The advantages of this method are easy to fit, and it also makes it really easy to visualize inhibition. So it makes it very easy to see how the Km and the Vmax change when you add an inhibitor. Because again, the intercept is equal to 1 over the Vmax, and the y-intercept is equal to 1 over the Vmax. The x-intercept is equal to negative 1 over Km, and then the slope is the change in the Km over the change in the Vmax. So you'll see in a second, it's very easy to visualize inhibition. However, there are some significant disadvantages with the Lineweaver-Burke plot. And in fact, it's debated, one of the things that's debated in biochemistry education is, why do we do a Lineweaver-Burke plot when these disadvantages are so strong? And that's because when you do the double reciprocal plot, you have your biggest errors at your smallest substrate concentration. And so what happens is, when you get a substrate, when you get a Lineweaver-Burke plot, you're going to have a bunch of slopes down here, velocities that are close together and have small error bars. But because again, those are going to be our bigger substrate concentrations, and the ones out here are going to, and as you go further out, you're going to go to smaller substrate concentrations. And so your smallest measurements, you're going to have the smallest slope. And so that means you're going to have a larger error because it's harder to measure a smaller slope. So you're going to have like 1 or 2 points that are way out there. And depending on the errors of that slope, it could be here, it could be here, it could be here. And so there's a lot of potential to skew your data. And for those of you who got different values for your activity units depending on your enzyme dilution, you know what I'm talking about. So the way that the nice thing about, again, this fit is you can pull out the Km and the Vmax easily from a linear fit. So if we have y equals Km over Vmax, that's the slope, or the m, times 1 over substrate, where 1 over substrate is going to be our x, plus 1 over Vmax, where 1 over Vmax is our b. So again, really easy to pull out the data. And if you did a good job with your kinetics, and you have a good linear range, your values should be very close together. However, flipping your data out, or by giving the double reciprocal plot and having your small enzyme concentrations out at the top of the line up here, introduces a lot of potential for variability. So now let's talk a little bit more about enzyme inhibition. So why do we care about enzyme inhibition? And I talked about this a little bit in the beginning, but many drugs are enzyme inhibitors. So if you're to read the literature on a particular drug inhibitor, there's a lot of different things that go on. But one of the first things that are going to be looked at is how that inhibitor or that drug affects the way an enzyme acts. Does it affect the speed? Does it affect the binding? All those things matter. And so the experiments that we're performing, looking at an inhibitor of LDH, that's directly applicable to other work that people have done with drugs that are enzyme inhibitors. Now, when I show you the different types of inhibitors, I'm going to show you an example of Lineweaver-Burke plots, again, because I mentioned Lineweaver-Burke plots are particularly useful for getting an idea of how enzyme inhibition works. However, the Lineweaver-Burke data itself should not be your indicator. So when you write your lab report, you can't say, this enzyme is non-competitive inhibitor because of the pattern on the Lineweaver-Burke plot. No, that's not enough. You need to discuss changes in Km and Vmax. If you were to write a paper and say, oh, this novel inhibitor of the enzyme XYZ is not competitive because the Lineweaver-Burke plot looks like this, you'd get laughed at. So when you do your lab reports, when you collect your data in class and you're making that judgment call and you're writing your lab report, you don't want to say, oh, it's because of the Lineweaver-Burke. You want to talk about the changes in the Km and the Vmax. That being said, let's move on and let's talk about the three major types of enzyme inhibition. The first, and perhaps the simplest to understand, is competitive inhibition. And so what happens with competitive inhibition, as you can see here, that the inhibitor looks a lot like the substrate, and the inhibitor competes with the substrate to bind to the enzyme to form the ES complex. So the inhibitor, if we add enzyme and substrate inhibitor together, we can either form the ES or we can form the EI. And so the inhibitor competes with the substrate to bind enzyme, an enzyme alone. And so what happens is then that because the substrate is competing with the inhibitor to bind, the amount of substrate that has to be present to achieve half Vmax is going to go up. So an inhibitor is going to increase or is going to change the Km or change the apparent Km because you're going to need to pump in more substrate to overcome that inhibitor. However, once the substrate is bound to the active site, the reaction velocity isn't going to change. So the Km is going to change with the presence of an inhibitor, but the Vmax isn't going to change. And so if we look over here again at Lineweaver-Burke plot, what we see is that the Vmax, the 1 over Vmax, that y-intercept, all the lines they're going to intersect in the same spot because the Vmax doesn't change. However, the x-intercept, or 1 over the Km, is going to change because the apparent affinity of the enzyme for the substrate will change. So the characteristic Lineweaver-Burke of competitive inhibition is when your lines intersect on the y-axis and then are spread apart on the x. So what happens with the next type, uncompetitive inhibition, is that the inhibitor binds to the enzyme substrate complex. So you can see here, first the substrate binds, and then the inhibitor can't bind until the substrate is there too. So the inhibitor binds ES and only ES. And so in this case, what's going to happen when the enzyme binds, when the inhibitor binds, it's going to affect both the Km and the Vmax, and it's going to affect them proportionally. And so in the Lineweaver-Burke plot, this is manifested by the characteristic plot where you have parallel lines. So the Vmax and the Km are both going to change, but they're going to be changed by the same amount. And so again, that would result and manifest itself in a Lineweaver-Burke plot of these parallel lines. And then the last type that we're going to talk about is non-competitive inhibition. And that's where the inhibitor can either bind the enzyme alone or it can bind the enzyme substrate complex. And so what happens in this case is when the enzyme binds both, but it doesn't necessarily, but whether or not it has a preference, it just depends on the enzyme and the inhibitor. And whether or not the Km and the Vmax are dependent depends on the type of whether or not it's pure non-competitive or mixed type. So what happens is when we have the pure non-competitive inhibitor, it doesn't have a preference for either the E or the ES. And so what happens is the Vmax is going to change, but the Km is not. However, there's almost never pure non-competitive inhibition, and this results in the mixed type. And so in this case, both the Vmax, and this is when the one type of an enzyme, so either ES or E is favored over the other. And in this case, both Vmax and Km are going to change with the inhibitor. It just depends on which enzyme complex is preferred. So in this case, the inhibitor could bind to one or the other, but it bound more strongly to one than the other. And if we look at the characteristic pattern for the Lineweaver-Burke plot, I kind of like to think of it as looking like a train wreck. And so again, there's the Vmax is definitely going to change. So those lines are going to intersect at are going to hit the y-axis at different points. But the lines are going to intersect either somewhere between the y and the x-axis, and that's if it's pure. I think if it's, or no, that's if it's mixed. And then, or they have the possibility to intersect actually on the x-axis, and in that case, that would be pure. Because with pure, the Km would not be affected, and so we would see it intersect on the x, whereas if it was mixed, the Km would be affected, and so we would see the lines intersect ahead or behind or ahead of the x-axis or behind it, so we would see different Kms or different x-intercepts for those lines. So I mentioned earlier that referencing the shape of a Lineweaver-Burke plot for inhibition is not enough evidence for selecting an inhibition mechanism. So I wanted to take a minute to look at what inhibition looks like on a substrate saturation curve. So this is an example where we have an enzyme substrate saturation curve without inhibitor in the blue, and then with inhibitor in the black. And so again, the Km apparent would be the Km that it appears to be with the addition of inhibitor. So in this case, for inhibitor, our Vmax is around 200. So our Km would fall around about 100 micromole per minute. We extrapolate down, our Km is about here. For this form of for the inhibitor, again, our Vmax is probably about the same. It looks like it's also approaching around, let's see, maybe around, looks like maybe it's approaching like 180, so maybe down to 90. So our Km is going to be different here. And so this would be our Km apparent. So again, the Km apparent is the Km in the presence of an inhibitor. But remember that Km is going up because the inhibitor is preventing the enzyme from binding. And so we can use the Km of the enzyme in the presence of the inhibitor and the presence and the Km without an inhibitor to determine the Ki or the inhibition constant. That's I guess I don't know if it's the formal name, but I like to think of it as the inhibition constant. Or the equilibrium, or the actual equilibrium constant of the enzyme for the inhibitor. And so to determine the Ki, the proper way to do it is to measure the apparent Km as a function of inhibitor concentration. So you would run a bunch of different experiments where you generated substrate saturation curves with different concentrations of enzyme inhibitor, and then you could take the apparent Km as a function of inhibitor concentration, and then use that to find the Ki, or the equilibrium constant of the inhibitor for the enzyme. However, in this laboratory, we have a limited amount of time, and we can't test, 5 to 10 different inhibitor concentrations. And so what we can do instead is we can do what these guys did here, and we can look at the enzyme without inhibitor and at one concentration of inhibitor, and then we can use the relationship between the apparent Km at a given enzyme inhibitor concentration and then the Km of the enzyme without inhibitor to then solve for the Ki using that relationship. Again, you can see how this would make sense if we had a linear relationship between the apparent Km and the inhibitor concentration, how this would make sense. However, we can't take a shortcut using one inhibitor concentration. And so that's the last thing I'd like to cover in terms of content knowledge for this lab. But just a reminder before we actually begin the lab this week, a heads up of what you're going to be expecting for what you're going to be doing in lab. So you're going to be determining the Km and the Vmax for LDH and lactate while keeping the NAD plus concentration constant. You'll determine the Km apparent and the Vmax in the presence of a given concentration of inhibitor. You'll need to use your data to determine the mechanism of inhibition and estimate the Ki for the inhibitor. And then finally, you're going to make two plots where you have the hyperbolic Michaelis-Menten plot and then a Lineweaver-Burke plot for the enzyme with and without inhibitor. So you'll have one plot where you have your lines. That's no indication of the mechanism, by the way. And then one where you'll have your two substrate saturation curves. And you're going to have to make these curves in sigma plot. So download that sigma plot. They need to have error bars. They need to have the proper fits, and then the fit equation, and then the goodness of fit, or the R squared in the caption.